So we're going to wrap up section 10.7 here, and we're looking at two more theorems which have to do with term-by-term differentiation and then term-by-term integration. So when we have a power series that has a radius of convergence r, as long as that r value is greater than 0, we're able to find it with a function on an interval of convergence. We've been talking about this. And theorem 21 says that this function f has derivatives of all orders inside that interval, and we can find the derivative by differentiating the original series term by term. Theorem 22 says that if we have a function defined by a power series that converges on this interval where, again, the radius of convergence is greater than 0, then we can find the, or we can integrate, and the integral is also going to be convergent on that interval of convergence, and we can find it just by integrating the function. So we have differentiation and integration defined for these power series, but how does that work in theory? How can we do this? Or how can we do this, not in theory, but in practice? So I'm going to look at an example here. It says identify the function given here. F of x is defined by the power series from n equals 1 to infinity, negative 1 to the nth, x to the 2n plus 1 over 2n plus 1. And if you start writing that out, you get x minus x cubed over 3 plus x to the 5th over 5. The next term would be minus x to the 7th over 7th, and so on. And we're asked to, again, to identify the function. So I'm going to start by using theorem 21, which is term by term differentiation. So I'm going to differentiate term by term, and I'm going to differentiate this here, okay, so you can actually see what we're doing. So differentiating, you now have this 1 minus 3x squared over 3 plus 5x to the 4th over 5, and I'll even go one more, minus 7x to the 6th over 7. Now I can clean this up a little bit. That's the same thing as 1 minus x squared plus x to the 4th minus x to the 6th, and so on. And this is actually a geometric series. So this is the geometric series where the r is negative x squared. So I'm going to start here at n equals 1, to infinity, and we've got negative x squared to the n minus first power. Okay. So when n is 1, we'd be raising it to the 0 power. Anything to the 0 power is 1. At n is 2, it's negative x squared to the first power, which is here. N is 3, negative x squared to the second power, you get positive x to the fourth, and so on. Now, the nice thing about a geometric series is that we can find the sum of them very easily. So we've got our r value of negative x squared. So the sum here is going to be 1 over 1 minus r, so that's 1 minus negative x squared, or 1 over 1 plus x squared. So again, this is the sum of the derivative of this function, but I want to go back and find the actual function, So now what can I do? Well, I can integrate. I'm going to integrate this sum. So integrating, we're looking at the integral of 1 over 1 plus x squared dx. And that is equal to inverse tangent x plus c. Now, we're almost done. All we need to do now is find the value of c, because right now f of x is equal to inverse tangent of x plus c. But we don't know what c is quite yet. But we can find it. When you're trying to find an easy way out, always try to go for zeros. So what I'm going to do is I'm going to look at what we were given here. We're given the function in series form. I'm going to look at f of 0. So we're going to look at the x value of 0. When x is 0, it doesn't matter what n is. All our terms are 0, okay? So f of 0 equals 0. And let me move over here and write this. Okay, and again, we can get that from just the series up here. We know that f of 0 is 0. So if we're looking at the inverse tangent of 0 plus c, that's going to also be 0. Well, inverse tangent of 0 is 0, so that leaves us with c is 0. So our function here is just inverse tangent x. And if we apply this process to inverse tangent of 1, we're going to get, let me come back here, where x would be 1. We get here, which gives us the number pi as a series. So pi over 4 is the sum. It's equal to inverse tangent of 1 of the series. And we're able to also write the natural log of 1 plus x as a series. This bit here is going to come in quite handy later in the chapter. And then I also have the alternating harmonic series sum, which is the natural log of 2. So, like I said, this bit here with the natural log of 1 plus x, that's going to come in very handy. The other thing that will come in very handy from this section is that 1 over 1 minus x, this was at the very beginning, is the power series just x to the nth power. We'll come back and use that later on in this chapter. But for now, we are finished with 10.7. We're going to move into some specific types of power series called Taylor series the next couple sections.